This next video here is about magnetic force on a current carrying wire. Up to this point, we've only talked about the magnetic field that is created by a current carrying wire and the direction of it. We haven't talked about any of the specifics, but what we're going to focus on now is the force that is created by that current carrying wire. Now, this is one where I think that visually it's much more entertaining. So when you guys come back to class, I will have a demo for you where I'm going to put a wire between a magnet, which basically makes a permanent magnetic field, and we're going to make it jump out of the magnet just by simply running some current through it. So I've diagrammed a little picture here. Okay, so if I've got a little horseshoe magnet, okay, and pretend that the horseshoe magnet is in the plane of the paper, there's a magnetic field that always moves from north to south. Okay, now if I were to lay a wire through that horseshoe magnet, so pretend that this wire is coming out of the page, okay, out of the page and into the page. It's traveling along this axis that my pen is making right now. Okay, if that was the case, and we had the field going side to side and the wire perpendicular to it and then along a different plane, there's a force that is created that would be acting straight up from that along the y-axis. So if we consider north and south to be the x-axis and we consider the current being the z-axis, then the force would end up being the y-axis. Okay, now what would happen is that wire would actually physically jump out of the magnet. So again, I think it's more impressive when you actually see it. So when you come back, I'll show you that. This is another way of trying to draw this a little more appropriately. These circles with the dots in the middle is supposed to mean that there's a field pointing out of the page. Okay, so the field would be pointing right up at the camera. Okay, the current in the wire here is moving to the right, and you'll notice that the force then is down. Okay, now this leads us to what's called our second right-hand rule that we've learned. Okay, I like to call this the flat wire rule. And it's a flat hand. Now the first one we learned was the curl rule, which is just the direction of the magnetic field around a wire. Okay, this is going to tell us the direction of the force on that. Okay, so if you take your hand and you lay it flat, in this particular one the thumb is the current, your fingers is the field, and your palm is the force. Now some people say, well, how come fingers isn't F, isn't the force? Well, try to think of it like this. If you're going to push somebody, you don't push them with your fingers, you push them with your palms. Okay, so that's where the force is going to be. Your fingers are going to be the field. They kind of look like lines anyways. Okay, so in this particular case, if we use this right-hand rule, and this is going to be very awkward to try to show you, but if my thumb is the current, and I push it that way, my fingers are the field pushing up, then my palm here is pointing back at me relative to this particular picture. Okay? Again, this is going to be something where I feel like we're going to need a lot of practice trying to figure out the directions of these things. Okay? But that is the second right-hand rule. Okay? So how are all these things related to each other? Well, it turns out that basically the force on a current carrying wire is directly related to, number one, the actual field. So the bigger the field, the bigger the force. It's also directly related to the current. So the bigger the current, the bigger the force. And it's also directly related to the length of it. So the longer the wire, the bigger the force. So pretty much straight up, it's F equals BIL, or F bil. Okay. Now that is if the current, oops, that shouldn't say N, that should say is perpendicular to B. Okay, so in this particular case, all three of these things are perpendicular to each other. Your thumb, your fingers, and your palm, if you lay them flat, are each at 90 degrees. There's 90 degrees between your thumb and your fingers. There's 90 degrees between your fingers and your palm, at least the direction the palm is pushing. Okay, and there's 90 degrees between your thumb and the force as well. Okay, so if that angle between the current and the field is perpendicular, then this is just the equation that you would have. Okay, if not, you have to include the angle between the field and the current. So if you do that, then we have to add in the sine of theta, and that's because as long as it's perpendicular and there's 90 degrees, the sine of 90 is 1. If it's less than 90 degrees, well, now we don't get the entire amount of force. Okay. Now, that also means that if the current and the field are parallel to each other, then we get no force. Okay.